This video is about the spanning tree protocol. Nowadays you find networks based on switches as you see in the figure on top of the slide. Since the reliable operation of networks is crucial for many organizations, redundant links are used to protect against failures. In LANs they do not serve for load balancing. In another video I have explained the learning mechanism of switches. It also contains the flooding that a switch performs if the destination MAC address is unknown to it or if it is a broadcast frame. In the following we see a situation where this leads to difficulties. In this scenario there is an end system B which is currently unknown to all the switches. End system A wants to send a frame to end system B. The frame is depicted as F in the figure. It is received by switch 1, which sends it to switch 2 and switch 3 because it does not know B and therefore floods it on all ports. So we have now frame F twice. Switch 2 does not know B either and therefore forwards the frame to switch 3. Switch 3 receives the frame 2 times. It forwards the frame received from switch 2 to the switches 1 and 4. The other frame is forwarded to the switches 2 and 4. Switch 1 and 2 get the frame again, and since they still do not know B, they forward it again. This goes on, so that at the end the whole network is busy with duplicates of the frame F. It does also not matter if the frame F arrives at B. However, if B replied to it, then the switches would learn the MAC address of B and then the flooding would stop. Nevertheless, a similar situation would also occur in case of broadcast frames without the possibility to stop it. The idea how to deal with this situation is to construct a logical tree topology. A tree is by definition loop-free, so that you do not have redundant paths. It requires a unique route, that is, one of the switches has to be selected as the root bridge. The spanning tree algorithm also dates back to the times of bridges. Therefore, I'm talking about bridges in the following. Starting from the root bridge, the tree has to reach all parts of the network so that each end system is still reachable. I'm explaining you the algorithm in a simplified manner. Each bridge has an ID with 8 bytes. It is composed out of 2 bytes priority and 6 bytes MAC address. In the protocol, it needs to be clearly decided whether an ID is smaller or larger. Therefore, the MAC addresses, which are unique, are included because they lead to different bridge IDs even if the priorities are the same. In a real network, it makes sense to set the priorities to influence the algorithm result. Then the bridges communicate with each other for some time using the so-called bridge PDUs. Bridge PDUs contain the current root ID, cost to the root, the ID of the bridge itself, etc. At this point, we take a look at an example. It is a situation during the course of the algorithm. Our perspective is the point of view of a bridge with the ID 10. The bridge gets bridge PDUs from neighboring bridges via its 4 ports, as you can see in the table. For example, it receives a bridge PDU on port 1. The transmitter ID shows that the sender of the bridge PDU is a bridge with the ID 33. The lowest ID that it knows for a candidate to become the root bridge is 3, and it can reach this bridge with cost 7. At this point, it should be mentioned that lower IDs indicate a higher priority. Bridge 10 compares the root bridge candidate IDs to find the lowest one. It turns out that the ID 3 is the lowest. Both bridge 33 and bridge 9 know a path to this bridge. The cost for the path that bridge 9 knows is lower. As a consequence, this is the best option for bridge 10 to get to this root bridge candidate. Bridge 10 provides information about this conclusion to the bridges on ports 1, 3, 4 by sending a bridge PDU with the contents 3, 5, 10. The 3 is the root candidate ID, 5 is a cost which is composed out of 4 that the bridge 9 has reported plus cost 1 to get to bridge 9, and 10 is the ID of our bridge. Now we resume looking at the algorithm in general. After these bridge PDU exchanges, the route is finally identified. Each bridge can then determine the least cost path to the route and select the port which leads to the route as so-called route port. Then each network segment is considered based on the ports that are connected to it. The port with the lowest cost to reach the route is selected as so-called designated port. All other ports which have not become route port or designated port are deactivated. These are redundant ports which have to be put in this passive state to avoid such loops as explained in the beginning of the video. Finally, there is a logical tree topology. The convergence time of the algorithm is 50 seconds, which is quite a lot, so that users notice once the algorithm has to update the logical network. There are improvements such as rapid spanning tree with a convergence time of 2 seconds. This is, however, still quite long in comparison to a limit of 50 milliseconds for wide area networks. If a network outage is shorter than 50 milliseconds, then users who are on the phone do not notice the outage. Otherwise, they perceive it. In larger networks nowadays, you therefore try to avoid spanning trees by adopting ideas from routing. Spanning trees have also the major disadvantage that larger parts of the network are unused because they are turned off. In addition, the paths which are used are not the best ones. Finally, we see here an example. In this network, bridge 2 has the lowest ID and is therefore selected as the root bridge. Then the spanning tree is constructed and ports on each other bridge are identified as root ports which lead to the root bridge. Afterwards, designated ports are selected so that each network segment can be reached with minimum costs from the root bridge perspective. Finally, one port on bridge 9 is neither root port nor designated port, so that it is blocked.